Hello everyone and welcome to the course. Today we'll be talking about the deployment of machine learning models. So if you recall the AI lifecycle, we go through various stages here and then now talk about how do we deploy these models in real world environments. But before we do that, let me shortly repeat what we discussed last time. We started with the initiation within the AI lifecycle where it was a lot about how do you get the right data, how do you pre-process it, and in the end, how do you make it digestible for algorithms? And then in the very last lecture, we talked about how do you choose these algorithms, how do you set them up in terms of training test split, which different options do you have at hand, what do you have to watch out for example, when you choose your evaluation matrix, if you choose your optimization mechanism, right? And the first thing that I really want to stress again is it's this very interplay of data and algorithms capabilities, and then also in the end on the performance metric that you choose, and that has to be regarded as a holistic phenomena. Second, it's important that you can and probably should optimize the parameters of your algorithms, and there are a bunch of options that you have at hand, also depending on each of these algorithms. But you have to watch out how you do that, especially that you do not overfit or that you enable data leakage. Third, we talked about selecting the right performance metrics. And again, I want to stress that they set the aim for your overall endeavor. So choosing them needs to be a very reflected thought process. And think again of your initial business problem here. So which performance metric addresses that initial problem that you try to solve in the real world? And then finally, and I think I said that already, is the interplay of these components of the problem statement, of the data, of its distribution, especially the one of the target, the chosen algorithm, and the performance metric. That's the important thing. So typically you would not look at these things in isolation, but within a combination. Now with this repetition at hand, I think we can look at the deployment step, right? And we came originally from the terminology and why it is important and interesting to deal with AI in the first place, and what we need to do in the initiation, modeling, and evaluation, and now it's all about the deployment step. The next step after that will be concept drift, which we'll cover in the next lecture, and this is all about how do we make sure that our models stay valid over time. And then we move into the logic of AI in systems in the next one. And the other view that I want to make clear here is the one from the agent, if you recall our definitions. So if we think about the capabilities, the environment, and the agent as a foundation for everything we do, then the deployment step is today about this box above there, right? Now it's all about how do we deploy this agent within this environment so that it can make smart choices in the end. And the other view that I want to look at is the AI lifecycle. So we covered the first steps. Now it's all about the model deployment. However, the model deployment utilizes steps that we covered earlier, specifically the model training, and also, again, in some cases, the model testing, but mostly it's about training again, although this time the goal is a different one. So the lecture's goal for today are, first of all, I want you to explore what are the phases that we have when we deploy a model now in the real world. Second, I want you to understand how to train that because it differs from the previous step. Third, I want you to familiarize yourself with the different possibilities that you have when it comes to deployment because there are many, especially as we moved more into the age of cloud computing. And then finally, I want you to be able to illustrate the different implementation options that we have at hand. But let's have a look at the steps that you need to do if you want to deploy a model. First of all, it's all about training a final model. Now, this step is interesting because it's not about evaluating the performance anymore of your model, but it's about training the best possible model. Once you've done that, you have to decide on the implementation option that you want to use, and then finally deploy it, and then again ensure its validity, which is something that we'll cover in the concept drift lecture. So let us first dive in and look into the final training. Before, in the very last lecture, it was all about an iterative process of model training and model testing, estimating the performances, overall gaining an approximation of the overfitting tendencies, right? How well is our model at capturing the patterns in our data? How well would it possibly perform in the real world? That was all of high importance because we wanted to build a model that captures the capabilities that are required in the real world. So that means all those data points, illustrated here as 3 ones, we typically use to train and sometimes to test. Now, the goal is a different one, right? We have an understanding on how well our model performs, which parameters work well, etc. So now it's about using all the available data, and we want to use that to build the best possible model to the best of our knowledge, to then integrate it into a productive environment, right? So before it was all about estimating performance, now it's all about building the best model possible. And the steps to do that are the following. First of all, we want to select the parameters for the final training. And there are a bunch of things that you can do here. So if you want, and this is purely optional, you can perform a final grid search. Again, using cross-validation, and then identify again the best performing parameters. But if you do that, you need to have the same search space that you had before. Otherwise, you would again have the possible tendency of overfitting. What you could also do is look into the cross-validations that you did earlier, the nested ones, because I assume that you did parameter optimization, and then look at which of these parameters perform best on average, right? And then make sure they also lay inside the confidence interval. So again, that you're not choosing anything that has the potential to be overfitted. And then you take those, right, this specific C and epsilon, or this specific amount of layers and neurons, and now you take them over to the final model training that is illustrated in this graph below here, right? So once we have these best performing parameters, we train the model with all the data, no more train test bit. We take all the data that we have at hand, build this final model, export it, and then deploy it. And then you end up with a deployed supervised machine learning model. And how you can do that, how we can do this deployment step, is something that we want to explore right now. Because we have to look at the different implementation options that you have at hand, and those changed over time. But before we do that, I want to give you a few insights on what the possibilities are when it comes to the autonomy of the agent that you're developing. Because what we should do here is distinguish between different levels that AI can have, right? And again, also which autonomy we want to give to the AI agent. And I want to differentiate into 4 different cases. Those are, in that sense, now conceptual and hypothetical, but there are examples of that, and that's something that we can also discuss in class. Now, the first one, the first level of autonomy, is a machine learning model outputting simple prediction results, right? This stock will go this direction, or this is malicious cancer in this CT scan, things like that. But it will only output results. The next step to that is a machine learning model outputting precise recommendations. So that's a change here, right? Before we said it's about predicting, now it's about giving recommendations. So things like buy this stock or treat it that way. And that is an interesting change in the autonomy that we give to AI, also psychologically. But what both of these cases, even if one is more extreme, require are only sensors, right? It can only sense from the data, it can make predictions and potentially recommendations, but that's about it. So that's where I want to draw the line, because then there is the case where a machine learning model could directly take action in some cases. Let's say autonomous driving. In 90% of the cases, the model knows what to do, because these are common situations that it encountered in its training in billions of data points. So it could take action in those. Or a different example, customer support. When you are using modern chatbots with your inquiry, then it's very typical that those are powered by large language models right now. And those models can cover a large percentage of the requests that come in automatically, right? It's simple stuff like, where's my order? I would like to cancel my order. You don't typically need a human involved there. Although we will discuss that deeper when we come to the human AI collaboration part. But that's the case over here. And then we have the final case where the model will always take action, right? So full automated driving, for example. And for these cases, different requirements are made. Also, if we look back at our definition of agents, right? For the one above, we only need sensors. It will only read and then will output prediction results or recommendations. Whereas in the other case, we need actuators where this agent can change the environment it lives in. And I want to continue this thought experiment right now. So let's say we're in the production line, and we now play with these different cases here. So now it's not only about the model itself, but we have an integrated AI agent. So now we call it AI. And this factory is producing some kind of goods. We see a table here with the output, the ones shipped to the customer, and those claimed by the customer because they are faulty. And let's assume for the moment that in the baseline we have no AI at all, and 10% of our products are faulty. So our factory outputs 100 units, 100 of those are shipped to the customer, and 10 are claimed, right? That is bad. That's something that we typically don't want. Let's say this company now decides to implement an AI which is either only predicting or gives precise recommendations. And let's say that's a good AI in terms of performance, so it's able to identify these faulty units with a very high precision. Let's say it detects all of them for simplicity now. Now, if we implement this would be case B. We would identify those, and those would not be shipped to the customer anymore. Great, right? So we don't have those 10 units claimed by the customer anymore, but we still, from 100 that we output through our AI-based quality control, we now only ship 90, but 10 are still faulty. And now let's say we implement an AI that is recommending precise changes of the parameters of this factory line, right? Not the parameters of the algorithm that we covered last time, but how, I don't know, temperature, pressure, right? Adjustments in this factory line, and the human is changing these parameters. And let's say it helps the human here and there, right? We could go up by 2 more units, right? So again, we produce 100, and now only 92 of them are perfect, and 8 are still faulty. And now we could imagine the case C, and that was the last one that we talked about, is now we have an AI that can also interact with these factory parameters. So it can change these parameters, and potentially, right, it could go up to 95 correct units, right? Of course, it could also go the other way. And that's something that I also experience in my work a lot, is in reality, of course, we cannot do that, right? We can't give all the parameters to an AI and let it play around in reinforcement learning style to find out what are the best parameters to reduce faulty products as good as possible. However, if you can simulate this in a very accurate way with digital twins, that might be an interesting case. And I don't want to leave with a standardized or generalizable comment here in the case of you do this or do that. I just want to make you sensitive to the fact that you have options here in what autonomy level you will give to the model that you developed. And I want to give one example from research that we did and that we published, which was together with the Schwarz and Kaufland group, which was about faulty packaging of coffee, right? You can see that over here. There are a few examples, like the expiry date is printed the wrong way. The lot, so the barcode is wrong. The top sticker is missing, things like that. And we did pretty much what we just discussed in terms of we built a quality control in there, which was powered by a computer vision model to detect exactly these faults. But we stopped, to be honest, at the B part, right? It did identify those cases, and now it was up to the humans to decide which parameters to change in the factory line. So that's interesting, because that's the first step to the next one. Then, if you want to read the paper, I'll make it available for you. And if we think about this even further, about humans having interventions on the processing, on the factory process. Again, how do we know who does a better job here? Who's better at changing the parameters in the process to make sure that the output is less faulty? Is it the human or is it the AI? And this brings up a very fundamental question. What are the roles of humans, of human experts in human AI collaboration? And I also thought about that a lot. And that led me at one stage to start with very fundamental research. And it dared me to ask the question, if we go back a step, who is better at a certain given task? Is it a deployed AI or is it a human? And to test that out, we built a bunch of different tasks, and we gave that to AI and we gave that to a human to find out who's better at capturing patterns in data. So you can see these kind of intelligence tests over here. They're at least inspired by intelligence tests. So we would give training rounds to humans and then test how well they learned the pattern. And we would also give this to a bunch of different machine learning models, also to test for the individual strengths and weaknesses. So if you want to, you can have a look and see if you can find a pattern here. So what kind of pattern determines whether this small slider below there is true or false, and then you could use that in the test set below there. So see if you can find the pattern. This is also possibly something that we can do in class again. But apart from what the precise pattern is here, what we did then is we looked at how many training instances does a human need in comparison to a machine learning model. And we did this to a bunch of models, as you can see down there, MLP, log-res, decision tree, and the human for comparison, which is the black line over here. And then you can look at how many training samples do you need to reach what accuracy level. And the interesting finding here is that we did that for a bunch of different patterns and for a bunch of different algorithms and with a lot of different people to make sure that the results are generalizable. And the interesting case is that we humans are really, really great at identifying patterns from very, very few data, right? So we only need to touch a hot stuff for once, and then we always know we learned what hot is. This no-shot or zero-shot or few-shot learning is typically very, very hard for machine learning models. Now, there are foundation models and newer inventions that also enable those models to do that, which we'll cover in the foundation models part. But if you take a vanilla algorithm, it's going to be typically quite bad there. But what we also observed across all these different tasks and algorithms is, while humans do learn fast, typically after a certain amount of training instances, they don't learn anything else, or they don't learn the pattern at all, right? Because of probably cognitive overload, right? We as humans can look at maybe 20 or 25 instances, but it's going to be tough for us to look at more than 40, and looking at millions of instances is very hard for us. Now, this is not the case for the machine learning algorithms, as you can see from this example over here, right? They continuously learn. So what I want to say at this point is, obviously, humans and machines have different strengths and weaknesses, and it's probably good to think about how we can utilize them later when it comes to the idea of human AI collaboration. But now, let's come back to our deployment challenges, and let's say we agreed on one of these levels on the degree of autonomy that we want to give to the AI. And there are a bunch of things that we now need to consider, and especially if we look into practice, there are many, many challenges when it comes to the deployment. The first one is we have multiple programming languages, things like Python, R, Scala, and they are used even for different parts of the same model. And typically you want to embed your model into some kind of software artifact. And this software artifact also consists of a bunch of different programming languages, sometimes hosted on a bunch of different servers. So how do we make sure that all of these different programming languages harmonize and they can all work together? The solution to that is APIs, and we'll get to that in a second. The second one is nowadays we typically use deep neural architectures, so deep learning, and this often requires a lot of parallelization. And that's something that is typically offered by graphical processing units, right? The graphics card of a machine, or short GPUs. And in the old world, that is rarely the part of existing core infrastructure, which was very much focused on CPUs. And you can see this in the demand for GPUs. You can see this also, by the way, in NVIDIA's stock, right? So there is a solution to that. Not everyone needs to buy GPUs. Of course, we can utilize the cloud. And then finally, we don't know how much in advance this model will be utilized in many cases. So it can have some kind of spiked or unpredicted pattern in its usage, depending on whether we have one user per week or if we have 1 million users per week. So making this cost efficient and also making it scalable is difficult, but there's also a solution to that called serverless. And now let's dive deeper into that, and let's start with the APIs. Now, API is a term that comes from software engineering originally, and it stands for Application Programming Interface. And the idea of an API is that it expresses a component, so a function, a program, in some cases also a machine learning model, in terms of its functionalities, its inputs and its outputs, and the expected underlying types, right? If you recall, like the Python basics, which is the data type? Is that a float? Is that a string? And so on. So it's the interface so that other components can work with it. And to do that, we need to understand what does it do, so its functionality. What inputs does it require? So does it require a bunch of text, a bunch of numbers, and what format? So what type? And then what will it output? What will I get back from that? Right? You can think of it as a transaction. And you can look at APIs because the developers give you these API documentations that tell you everything about it, right? You can see an example over here from ChatGPT, right? Which tells you exactly, for example, what role does the human play here? What is the content? And you give it that kind of strings. If you look into the API documentation, not only of ChatGPT, but of any service out there, you can see of what does it require. And the example is one right over here. So this gives you a feeling as another developer in what is required of you and what can you expect back. And now we talk about our own models. So that means we also want to design that API so that other services can use it, and also that ours can be used as a service, right? And the great thing about the API is that it makes it programming language agnostic. So I can have a Java component over here and a Python component over here, and they can talk to each other because the way that the inputs and outputs are transferred are standardized, and this gives us a lot of opportunities. If we look at a brief history of APIs, and by the way, those are only the ones that are public. You can see which are the most interesting ones. You can see, for example, how Salesforce as a B2B operator is the most common one. Then we have things like WhatsApp and Twitter. That's a little bit old in terms of the statistics. It's from 2023, but still gives you an idea. And these are all called, by the way, so-called RESTful services, which is a standard that is well established to make sure that these different APIs can harmonize and can talk to each other. And if we look at the history of APIs, you can see that this really enabled a boom in terms of, some people call it the API economy, because once you develop now something, you can, the only thing that you have to do is define its functionalities, its input and output, and the data types, and then everyone can use that. Which is something we'll come back to because it's very important. It's a cornerstone of cloud services, right? So we see APIs work well. There are a bunch of public APIs. There are even more non-public APIs. If you look at like a service like Uber, for example, has 5,000 APIs, but none of them are public. It's the way that the platform organizes itself. Sticking to Uber, I think an interesting case of a so-called API mashup or service mashup is Uber in general, or also Uber Eats. So you have the end user on the one hand, the buyer, that interacts with the solution Uber or Uber Eats in this case. And now Uber, of course, was left with the question, how do we get all this map data, right? We don't want to build our own map service. So they use the API of a service provider. In their case, that is Google Maps, right? So you recombined existing ideas in this case, the idea to order food with an existing service of maps that Uber Eats didn't have to take care of. And by the way, of course, it was clever for them because they already had the Uber app running. But that shows how in the API economy, you can recombine different existing services, different APIs, to create something new. But the question now is, of course, what about your own build models, right? That were examples now from practice. Well, there's an easy way out because you can utilize software that does everything for you, right? You build your entire pipeline with tools like BigML, IBM Watson API, Google Cloud Vision API. There's stuff from AWS that gives you those options that you directly work in this environment where these services can then be deployed. But what we want to look at now is the services that you can develop yourself, and those were built in your own local Python notebooks. So the question is, how do you build your own, how do you design your own customized API? And there's a very easy way to do that. That's called the Flask framework, and that does literally everything for you. So it provides a RESTful API. It does everything for you. It loads the machine learning model. It creates the route, prepares the scoring data, runs the prediction, does the post-processing, and returns the result. So Flask is a great package that allows you to export your own machine learning models and run them as your own RESTful web service. And that's something that we will try out together, right? But that's the missing step in terms of you had your code and your model that you fit to the data. Now this is the way that you can use this model to make predictions in the real world by providing it with a RESTful interface. We'll cover that in the exercise, and you can do that and run through these steps on your own. For now, let's assume that you did that, right? You built your own model. You potentially used Flask to create the API, and now you want to know, how do I make it productive? How do I put it into the real world? So let's talk about deployment options. There's the old way on how to do that. That is the monolithic one that I'll explain in a second. And then there's the modern one, which deals with microservices. And when it comes to microservices, we need to ask two questions. The one is, which components are needed to control, deploy, monitor, and run the services? And then you have a bunch of different cases here that we go through. And the other question that you might want to ask is, how do you encapsulate these deployment environments from the physical components, from the hardware? How do you detach that? But let's first start with a question on monolithic versus microservice. And this brings in logic that we call service-oriented computing or model-driven programming. Sometimes it's called service-oriented architecture. But I want to shortly explain to you what that is. Let's go back many years, 70 years, and look at the way that software engineering worked then. What we had there was called monolithic programming, or coders call it spaghetti code. And let's have a simplified example, the one of a banking transaction. So what the programmers would do here is they would have multiple checks, and those code would run from the top to the bottom. So it would check the ID of the customer, then check the balance on the banking account, then perform the transaction, and then provide a receipt, right? This was all one step after the other in your code for this case of the banking transaction. And that's what we would call a monolithic program. Now, over time, software engineers saw that they would redo the same type of task over and over again. For example, checking the balance is not only required in this banking transaction here, but also, for example, if you want to have a meta report of all your customers, things like that. So what they started doing is they moved out one component of this monolithic logic here and used reusable pre-programmed components, also called services in the realm of software engineering, right? And those obviously had that API that we talked about, right? It needs to be well defined in terms of what input is expected, what output is expected, what are the underlying data types, and what functionality does it provide. In this case, it's checking the balance. So that single component could be reused and reused in other cases as well. What then happened over time is there were multiple components that were encapsulated within services. And you can already see a shift of the way that we work here, right? In the monolithic way, it was all about programming, coding. Now it's less of programming, but more using of pre-existing, predefined components and services with well-defined interfaces. And today we are in the world of many components, so an extensive use of components or services. And that's interesting because when you develop a program right now, it's become more of a modeling or choreographing than about knowing everything by heart and coding it down, because we use so many predetermined services. And I think in the end, it's also an analogy to how we deal with supervised machine learning right now, right? Many things that you do are encapsulated within packages, right? You don't have to do that work. It's only a few lines of code left. Whereas when I started with my PhD, you had to do more or less everything yourself. I mean, there were packages, but not as comprehensible as they are now, and also as comfortable. So you can see this shift from a monolithic program over to a service-based program on the very right, where it's only about a combination of pre-existing components. Nowadays, this idea is mostly called a microservice architecture. So microservices are the next step in this evolution of service-oriented architecture. For you, it might seem the way that microservices and services are the same. Well, technically there is a difference. I think the best definition is that a microservice is much smaller and it typically focuses on a single, very specific business function. And also is completely independent of the other one. So there were some still monolithic concepts attributed to the old logic of services, but now a microservice is really an encapsulated single specific business function. They use a bunch of standardized interfaces like HTTP, REST, or so on. But the important thing is that you see that we now move into this overall microservices architecture, where you have a user interface on the one hand, and then an orchestration of many, many microservices. And if you look at recent quotes, there's one from Gartner from 2023, which says that almost 3/4 of respondent organizations are currently using microservices architecture. So this has become the standard in how you design large artifacts, especially those based on machine learning. And it's now, from this other quote over here, it's the natural paradigm for developing a machine learning pipeline. So deploying your model as a microservice is the natural, most modern way to do that. Okay, now let's say you agreed that you want to do a microservice. The question now is, which components are needed to control or monitor deploy and run these services. And there you have a bunch of different options at hand. Let's start on the very left here. Let's say you do it on premise. That would mean you have your own hardware, your own local machine in your physical environment. You plug it into the internet and everything runs on it. That means you have the hardware, the physical server. You have the host operating systems, all the bins, all the labs, all the data, all the applications running on that single system. That's what we call an on-premise solution. Now, this is a lot of manual effort. If you want to, especially if you want to build large products and scale that, right? Having 100 servers that you manage yourself in your server farm requires a lot of effort and your own technician probably. But also the customizability is very, very high, right? If things go wrong, you can simply unplug it and everything is, for the moment at least, not functioning anymore, and you can take your time to fix it. This is a traditional way there, right? That's how traditionally services were hosted. And from my experience, I can say that there are still cases where companies want that, especially for data protection and legal reasons. If that's always the best reason is up for discussion, but I think it also has a lot of psychological attributes. Anyhow, if we now move from the left to the right, the next step is infrastructure as a service. Now, here the hardware is somewhere else, in some kind of computational center, not necessarily in the same city or same state or even same country, but somewhere on Earth. Now, you as a developer, you're still responsible for hosting your own operating system, the bins, the labs, the data, and the apps on top of that, right? You lost a little bit of customizability here, but also you lost a lot of manual effort, right? You don't have to deal with hardware failures. Again, the service provider takes care of that. Then the next step is platform as a service. Now, you don't have to worry about operating systems or bins and labs anymore. Now it's all about your data and your application that you host there. Again, you lost a little bit of customizability, but also less manual effort. And then we move into a very modern paradigm called function as a service. Now, you only have single functions, single microservices, which serve one specific business function. That means not even data is hosted there anymore. And then finally, you have software as a service, which is a very, very broad term. That could be even an app on your phone, which only interacts with an API that is hosted somewhere, right? So you can see there are many options for hosting microservices, and it depends on a lot of requirements and specificities that we cannot detail out here. But for the moment, I want you to know that you have these different options at hand. Now, let's have a look at different cases from the real world. If you look at infrastructure as a service, so which is all about the provisioning, the processing, the storage, networks, and other fundamental computing resources. Now, you as a consumer, if you would buy that, you're able to deploy and run your own arbitrary software, right? Including your operating system. Let's say you need a very special Linux or Microsoft Windows operating system. You can choose that because maybe only this runs with your application. That gives you a lot of control. However, you do not manage or control the underlying cloud infrastructure, meaning the hardware. And there are a bunch of cases for that, right? There's Amazon, there's IBM giving you these options, even Google, and a bunch of more. So again, very much control, but you don't have the hardware. If we move over now to platform as a service, we can start talking about so-called cloud platforms. Now, they have the capability for you as a customer to deploy onto this cloud infrastructure using many things like different programming language, libraries, and so on and so on. You can set up the precise configuration settings, but you do not manage the hardware, the operating system, the network, the storage. This is all taken care of. And best example for that is Salesforce or the Google Apps Engine. Now, if you move even further down the line, I already mentioned that briefly, is the idea of serverless, or also called function as a server. I mean, serverless is a little bit misleading because, of course, in the end, it still does run on some kind of server, but the idea here is that you have to worry less about the servers here. So that is a model that is running pure programming code. Best example is all the Python notebooks that you did. You could deploy them as a serverless function. And the service provider deals with everything, with every physical or software components beside the actual function. And this has a bunch of advantages, and we can see a huge increase in people using serverless architectures. So first of all, you only pay when the function is running. When it's not running, you have no costs for unused servers. You don't have to worry about server management and security. Deployment is really, really simple. You only need the code snippet and then put it into the notebook. And it scales seamlessly and almost unlimitedly. I know that because I worked a little bit on these topics. I listed a source here, which I'll also give you access to, where we worked with machine learning in the background to optimize for these serverless environments. So we knew when would which customer want to scale up the functionality. So interesting case, because we now utilize machine learning to make serverless better. But you see, there are many different applications, right? Of course, this also has some downsides. You can, if you need like extensive data, that doesn't work because it is only a function. You can say it's a microservice in its purest form. The other question that we have to ask now when we deal with the microservices is how do we encapsulate now the deployment environments from these physical components? And if you recall the logic that we had earlier of on-premises, infrastructure as a service, and the other cases, platform as a service, function as a service, and software as a service, there are different cases on how we can deal with that. The first one is you have everything as a single instance running, right? It's all one. Again, very traditional, but that means you have to take care, again, depending on the chosen infrastructure, that you have to take care of the hardware, the operating system, and so on. Now, over time, people started developing something called virtual machines, and those provide the basic functionality in terms of having a host operating system and a hypervisor, and then you only load another virtual machine which captures all the applications, your data, your bins, and your labs, and your guest operating system into one so-called virtual machine that can then be run on any device, right? So you could create a virtual machine of your program code, for example, on a Linux environment, and then simply deploy it to any other machine where you can run a virtual machine, a virtual environment. So you're virtualizing this functionality. And the next step of this paradigm are containers. And now containers encapsulate, again, the functionality, a lot of the dependencies in one file in the end. And then you have a container engine which takes care of orchestrating all of these containers. And that's the most typical way to go as of now, I would say, is to encapsulate your microservice as a container. So containers enable an abstraction level, you could say, of applications. So you detach the functionality from the environment in which they run. So you end up with a single application that includes all of its dependencies, right? In your case, those would be all the packages that you would require are part of that, but without the full operating system that you need to run, right? You want to have all the dependencies that are required, but you don't want this entire baggage of an operating system. And this gives you a lot of cool options, right? It's portable. You have a single file that you can put on any machine that runs containers. It's very efficient because it does not use an entire operating system, because that part is emulated by the virtual machine or by the container manager. It gives you a consistent environment, so every application runs in its own sandbox. If one crashes, it has no impact on the other ones running. And the way it's designed is you can scale it easily by assigning more resources to one container or duplicating existing containers to the same container engine. And one name that you should have heard here is Docker, because it's the most well-known container provider. It has a standardized container file format that, again, really, really helps. And it's something that we also try to do in the exercise if we have enough time. It's some cases a little bit of a pain to set up initially, but once you get it working, it's very powerful. Now, in the real world, when we talk about large technology providers, they work with many containers, right, with thousands. So having your own containers always set up and run in a manual way doesn't work for them. So they need a system for managing a bunch of containers, you could say a bunch of functionalities. And one name that you should have heard here is Kubernetes. So this enables you to deploy, to maintain and scale all of your containerized applications. And typically also across multiple host servers, across different countries, different infrastructures. And the way it works is that it has so-called pods. Those bundle several containers on the same host server, so on the same physical server. You have nodes. Those, again, bundle several pods. And then all of those nodes combined are called a cluster. So if you ever hear the word Kubernetes cluster, you now know this is a combination of nodes, which then consist of multiple pods. And these clusters are controlled by the so-called master plane, right? It communicates with the different clusters. It schedules the task. When will you run which type of container? And you can see that this is only the logical next step of this way from monolithic programming towards scalable, service-oriented architecture of microservices, right? That's the way that many tech companies run their services right now. One other thing that I should mention here is, apart from Kubernetes, which is about managing the containers, is Cloud Foundry as a platform as a service, which is not only about deploying, but also about developing, right? So you develop your entire application in Cloud Foundry, which then also gives you the opportunity at hand to scale those applications, right? So it's you could say an integrated solution from development up until deployment. So it tries to cover all of these. It also has a bunch of other things, like it includes a marketplace where you have other applications. So in the end, other APIs, other microservices that are usable, right? Nothing that we'll use here, but you should at least have heard about that. One more thing that I should mention is, now, of course, there's also the option to do everything we do manually right now as part of the exercise of this course in the cloud and have so-called machine learning as a service. And there are a bunch of solutions for that as well, right? Like Azure Machine Learning Services, something that I personally also have used in customer projects, Amazon SageMaker, IBM Watson Studio, right? These give you the option to deploy managed services and do the entire development also in the cloud, and it will take care of everything for you. This is very common to be used in business. However, as this is an academic course, we also want you to do everything by hand once and do it locally and understand how would you, in theory, run your things locally. Okay, now, with these things at hand, I think we can have a look forward and look into the next and also last aspect of this lecture, which is machine learning operations. And I want to cover this topic because it's very dear to my heart, and I spent quite a lot of time in my research on that phenomena, so I think it's worth mentioning here. But let me motivate first, why are we talking about machine learning operations, or short MLOps, in the first place? Very much what you can see here in this lecture, in this course, is a critique that I typically also express towards other courses, so I'm a little bit guilty as charged here myself, but when you look at what data scientists are typically taught, it's Python code, right? It's, okay, how do you split your data? Which algorithm do you choose? How do you evaluate it? And so on, right? Typically, a lot of courses also stop right there, right? It's not about deployment and all the other things that we cover. So maybe we're a bit more advanced here. But when you move in the real world, and that's something that I did myself, is, that reality looks different, right? The machine learning code is only one piece of the puzzle. You have so many other options here. I think you understood that also from today's lecture, like the data collection, data verification, the serving infrastructure, the monitoring, the process management tools, feature extraction, configuration, right? And the entire product that you're working on is complex, and the code is only one single part of that. And machine learning operations appreciates that, right? And I have the definition here. I'm not going to read it out entirely. I'll link the paper to you. But MLOps, or machine learning operations, it's a paradigm, right? A way of thinking that includes aspects like a set of best practices, a set of concepts, a development culture when it comes to this end-to-end process, this end-to-end conceptualization, implementation, monitoring, deployment, and scalability of machine learning products, right? It's about building machine learning products. It's not only about the code where 99% of people talk about, but it's this entirety, this end-to-end process. And I want to cover this at least briefly as part of this course. It's hard to have an exercise that could go through all of these steps. That would require, I think, 2 days or so, but I want you to be aware of how machine learning products are developed nowadays, and MLOps is a very important paradigm here. And it has a bunch of important principles and then components implementing these principles, right? Continuous integration, continuous development, for example, an orchestration of the workflows, allowing for reproducibility, right? P3, a versioning of data, of code, of model, right? So it can revert back potentially. Collaboration mechanisms, continuous training of machine learning. We'll learn in the next lecture why this is important. A metadata tracking, continuous monitoring, and also feedback loops. And these principles, these 9 core principles that we also identified in research, are then implemented in these components that you can find as part of the MLOps architecture that I'll show to you in a second. It's not about understanding those details right now, but it's important that you understand that there are principles that developers work on nowadays that find their implementation in precise components. And speaking of these people, we also identified the important roles that you need right now for successful machine learning operations. And surprise, it's not only data scientists, but we have a very diverse group of people working here, right? The machine learning engineer is important, right? He or she is someone who is responsible for the cross-functional management of the machine learning environment and the assets, the infrastructure, the models, the workflow pipelines. But that's only one role. You also have the data scientist, which will develop the machine learning models, right? In the background, do the training, do the testing. You have the data engineer, who is responsible for the entire data management, the pipeline management, the feature engineering, and so on. You have the software engineer, who applies design patterns and coding guidelines to build the best possible product. You have an own development operations engineer, so a software engineer with DevOps skills, and DevOps is the paradigm of developing and operating solutions at the same time. So DevOps. And this person also manages the pipeline orchestration, the management, the monitoring. And you have a backend engineer who does all of the machine learning infrastructure management. And now in reality, unfortunately, many times this is one role, right? One person doing all of that. But in the ideal world, you have these separate roles with their separate responsibilities, because only if you have that, you can truly build a functioning, productive system. And I know this is an overwhelming graphics right now, and I can't get into detail, but the idea is that we do have an architecture and workflow for how machine learning operations works. So how do you build productive ML systems? And as you can see in the legend down there, we need a bunch of different roles to make sure this is the case. And typically, again, if you only have one person doing all of that, that's not a good utilization of the capacity that you have at hand if you really want to build continuous products. And in the next lecture, we'll also dive deeper into why it is so important to have a machine learning operations architecture and not have it in the traditional way, right? Everything is coded from top to bottom and then deployed, waterfall model. No, machine learning operations said we have a continuous running of developing our machine learning solution, a continuous deployment of that solution, and a bunch of feedback loops that ensure that our solution is always up to date and is in fact functioning, right? It would be too much to go into detail now, but I recommend to you to look into the paper. I'll make it available and then see how this works. And that's the way that we build, deploy, monitor modern ML products. Okay, now let me summarize. First of all, starting the deployment with a final training is important, right? You want it to be operational, and you want to use all the data that you have at hand to build your final model. Again, it's not about evaluating the performance anymore, but it's all about building the best possible model that you want to utilize in your productive setting. You have to think about the degree of autonomy that you want to give to your solution. So does it make decisions in the real world, or does it only put out recommendations or predictions, right? With the pros and cons that we briefly touched upon. Third, you have to think about the deployment options. So there are a bunch of different choices. there's not necessarily a right or wrong, but do you want to use a microservice? If so, what kind of architecture do you want to look at? And then look also at existing platforms that support you in doing that, right? Again, Kubernetes, Cloud Foundry, or even holistic machine learning as a service solutions. And then finally, machine learning operations gives you a paradigm that looks at this entire step of developing, monitoring, deploying your model in an end-to-end process. And that's really the way how it should be done today if you're building ML products. Okay, so that was it for today. Thank you so much for your attention and see you soon. Bye-bye.